76 dew points. You can't see this too well. 80-something temperatures back in here, 84. Really moist. Capes, 3,000. Over 1,000 back here. One of the studies on hurricanes said if you get a cape above 1,000, look out. If you have the shear, that's really good. But we've got capes just nearby, 1,500, 1,000. It still, as it moving north, you can expect some of that to keep changing. So pretty good looking. 400, the storm relative humidity, 400. What's a number you'd like to see for extra for tornadoes and regular storms?
I'd like to see 500, but I know the 2%.
Yeah, well, 250 is pretty good.
0 to 3 kilometer, about, yeah, 250. 250
is pretty good. So 400 is real good. This is just one day's worth, all those tornadoes. So one of the things you have that you can look at to help you along is go to the SPC site, and you can actually look at some of these fields and get an idea for the helicity and the cape. And if your cape gets above 1,000 and you've got helicity of over 250, think good. If it's 400, think real good. And if it's 500, again, there's orgasms going on from some of them.
Take cover over there.
Yeah, folks. So to summarize tropical system tornadoes and cyclone tornadoes, pay close attention to feeder bands associated with the bands. Low-level shear is maximizing the right front quadrant, so is the helicity. Generally occur where the convergence expands locally near the coast due to frictional convergence, where rain bands merge with other convective features. A lot of times it is where that bright blob is the brightest, but there's no guarantee. Maximum reflectivity isn't going to look that impressive. It's going to be a blob a lot of times. However, the reflectivity is often higher than surrounding areas. May not have a hook, a viewer, or any of those nice looking things, but you very often will be able to see it on the, if you're looking at the velocity data from X-ray. Now to the subject dear to my heart, maximum rainfall with tropical cyclones since 1971. This is from Dave Roth. I worked this storm when I was in satellite doing satellite estimates. 48 inches of rain. I hated it at the time because all I did is use tracing paper and pencils and keep tracing stuff. But you can notice everywhere in the east has big rainfall maximum. Everywhere along the tropical thing. As you get back over here, not so good. But even in California, 14 inches. So even down there, you can get big ones. Almost all of these western ones are associated with the entrance region of a jet stream. And we'll show you some of the East Coast versions of that. So factors that impact the rainfall distribution with landfalling tropical cyclones. Storm track, of course. If the storm track's different than forecast, it's going to make a big difference. That's one of the troubles for HPC. We're locked into we have to model we had to model, since I'm retired now, our QPF to the model, to the Hurricane Center's forecast storm track. That's something to be consistent. We have to do that. We can't go off and say, well, they've got it in Texas, I'm putting my max in Louisiana. That wouldn't look good. The time of day. That's not as important along the immediate coast a lot of times with strong storms, but as they start to decay, time of day is really, really important. And a lot of times, the core rainfall occurs at night when everybody is driving with their lights on and can't see very well. Storm size. The bigger the storm, the better, especially at landfall, but even that can be kind of misleading. Topography, wind shear, that's a negative, but it also can impact the distribution of rainfall. We've seen that a lot of times in convective stuff. When you look at a sheared event out over the ocean, where's the convection? It's on the east side. And synoptic scale features an extratropical transition. That means that when you get synoptic features associated with an upper level trough, you can have the characteristic of the storm change remarkably and really dramatically. One of the first studies of hurricanes that I came across was Goodyear When they make landfall, the heaviest rain is usually on the east side, a little east of the big eye. And that makes sense. Where would you have the flow coming into the land and frictional convergence? It'd be this side of the storm. Back here you have winds this way, so you wouldn't have the frictional convergence to help enhance the rainfall rates in the upward motion. Also time of day, this is Aaron. You can't just, when you're doing QPF for a storm, you can't say, okay, my hurricane's going to track like this, the remains of, so I'm going to have a continuous strike of rainfall, like that. It doesn't work that way. Maximum landfall, maximum here because you got hill country enhancing it, maximum here at night, maximum here at night. So you've got different things that can drive it. You have to think of those things when you try to make a forecast. And in this case, the models were abysmal. They took the storm like that and weakened it.
Great sound effects, by the way, there.
I've worked on that over the years. Storm size. Why would storm size be important? Just the heavy rain with the CDO is going to last longer with this storm if it gets over land than this little guy. If you have the same forward motion. So that's a no-brainer. We can get an estimate at landfall from the tropical rainfall potential technique. This is based on the DMSP SSMI rainfall rates. So it's a satellite rainfall rate. They can measure the rainfall rates, use the Hurricane Center's track, tell you how long it's going to be over land back over here, and give you a forecast based on the storm size, the rainfall intensity, but it assumes a steady state of a hurricane. And that's a kind of scary assumption. It doesn't always work. But for one big storm, one of the Allisons, the many Allisons, it seems like every Allison hits Houston. Here's one forecast, the Ada, max QPF 4 inches. Trapp said there would be 12 inches, and it pretty much was 12 inches. So it can certainly help when you know the model. I mean, 4 inches for a tropical system that's coming in, that's pretty paltry. You want to have more. Size, here's Francis. You can see how sometimes storms, as they track, take on different things, drive the rainfall. Where max is, here it is, the typical max on the east side, east side, east side, east side, east side. Now it's getting enhanced by the mountains, enhanced by the mountains. West side of the mountains, there's a min. What's happening over here? Guess? Any guesses?
Seashore front?
Yes, the front, maybe not a city. The front's forming. As it goes here, the front forms, then we start getting rain on the west side of the front. We get overrunning rain, just like you would have during a regular wintertime event. Vertical wind shear, as I said, if you have shear, very often the heaviest rain will be on the east side. It also helps weaken the storm. Rules of thumb, many of you have heard of the Kraft rule. The rainfall for the storm is going to be equal to 100 divided by the forward motion in knots. I hate that rule. I just despise it. And the reason I despise it is because it makes some assumptions. One, all storms are the same size. We know that's not true. Also, all storms are symmetric. We know that's not true. And it doesn't count fronts. One of the things I hated when I watched the Weather Channel about Floyd, one of their meteorologists got on and cited, this isn't going to be a big rainfall producer because of the Kraft rule says blah, blah, blah. Well, it had a front, and you can ask Sean how much rain he had.